Greetings, everyone. This is Group 16 of RES 1012 OL51. And for the presentation of research project, Design and Manufacture of Vertical Axis Hydrokinetic Turbine for Riverside Applications to Small-Scale Power Generation using Additive Manufacturing. The background of the study will be presented by Froi and Jimenez, me. The statement of the problem and the objectives of the study will be presented by Casandra, Klaire, de Cruz. The significance of the study will be presented by Gunhi. So is the scope and limitations presented by Gunhi. The related literature and theoretical considerations will be presented by Franz Ragasa. And once again, the methodology will be presented by Froi and Jimenez. The background of the study. The Philippines is a developing economy. Its people can now afford a high level of living, and the people's demand for energy is growing along with its economy and the population, although it must be noted not everyone has equal access to electricity. According to BIME 2014, approximately 12% of the population do not have access to electricity currently. Another issue is that the electricity prices in the Philippines are very high compared to other ASEAN countries, leading some foreign investors to choose to invest in other countries rather than the Philippines. Although the world is currently banking on renewable energy to solve its current issues with fossil fuels and global warming, um, they are still quite out of reach for developing countries like the Philippines. Although the Philippines has a unique geographical position that allows it to have multitudes of rivers while being in the Pacific Ocean. Therefore, it would make sense for the Philippines to utilize hydroelectric power massively. And it makes sense because hydroelectric power allows the user to generate tons of electricity for very minimum cost because it's just water flowing through a turbine. Although the areas that you can put them is very rare indeed. There's only a few in the Philippines and they don't even create half of the current energy matrix supply that the Philippines uses. As such, we the researchers proposed to equip the Pasig River with a vertical axis water turbine or a hydroelectric turbine because the Pasig River has a considerable flow rate caused by varying altitudes of light because it runs through the heart of Metro Manila area. This flow rate ranges from 12 cubic meters per second to 275 meters per second depending on the time of the year when it's raining or it's flooding. Nonetheless, its low flow is still viable for operations of vertical axis water turbines. Another consideration is that, according to the DNR, the Pasig River is considered a Class C river system, meaning that it can be used for fishery, recreation, manufacturing processes, and there are no restrictions on the installation placed within the banks of the river, unlike wildlife reserves. There are also considerations to be made on the size of the blade, since water is navigated by ships and barges. So a horizontal axis hydrokinetic turbine which makes up a significant amount of space, may not be an option. Vertical axis hydrokinetic turbines offer to be a cheaper source to manufacture as it requires no synchronization gear and since it's also omnidirectional. Another cost-saving measures because it's necessary for developing countries like the Philippines to ensure that the power source that it gets is as affordable to it as possible in order to maximize gains that could be seen. Therefore, the most expensive part of the blade, the turbine, the blade, um, the researchers theorize use additive manufacturing, 3D print the blades because it's usually the most hard to manufacture. It's usually the most expensive because it requires tenuous amount of strength, although not that much compared to hydrokinetic turbines that are horizontal axis. So they would be used to power the streetlights along the river. It'd be used for small scale power generation in an affordable and sustainable manner. And that is a benefit for the LGU, benefit for the Philippines, benefit for the researchers.
We will now proceed to the statement of the problem, the main and the specific objectives of the study. The objectives of the study is to design and manufacture working vertical axis hydrokinetic turbine which can be used on a river banks to generate enough electricity to support an lead street lamp or the other small-scale power generation requirements with the part of manufactured using additive manufacturing and polylactic acid. Specifically, the study aims at general objectives is to aim to design and fabricate a working vertical axis hydrokinetic turbine with turbine blades manufactured with additive manufacturing for riverside applications along the Pasig River. And with the specific objectives are to design a vertical axis hydrokinetic turbine assembly and turbine blades using computational fluid dynamics or CFD with ANASYS. And also to manufacture the created, design, and fabricate the turbine blade design using a 3D printer with polylactic acid filament. And the last is to deploy the manufactured design in a non-permanent fashion along the banks of Pasig River with a lead street lump and compare the following to existing zero-head hydrokinetic turbine designs with a cost, size, and the turbine power coefficient. The Philippines is a developing economy. Its people can now afford a higher standard of living, and naturally, the demand of the electricity in the country keeps increasing as the economy and the population grows. But it must be understood that a portion of the population does not have access to electricity. That means importing dirty, non-renewable energy from other countries. Energy sources other than oil and coal are undiscovered, but access and production are more costly. Said by Brahim in 2014, due to its location, the Philippines may employ hydropower as a renewable energy source. Hydropower harnesses the power of flowing water. When used appropriately, it can provide a lot of energy. By Gomil and Lee in 2020, hydropower can also help ease energy insecurity and reduce carbon dioxide emission.
Significance of the study. Why is our study needed? So, the aim of this research study are meant to give information regarding the usability of vertical axis water turbines on the Pasig River. The rising demand for electricity and excessive pollution are driving this problem. This research will also reveal the 3D printed turbines' suitability for small-scale applications. The computational fluid dynamics, or CFD, will offer information on the intended turbine's functionality. Furthermore, because the turbine design in this research project will be compared to current existing turbine designs, the study's findings may be very valuable for comparative design studies of hydro turbines. The cost, size, power, production of, and efficiency of the turbines will also be compared. Future researchers and local governments can all benefit from the study's findings. For local residents, this study may pave way to the small-scale utilization of vertical axis water turbines for local energy generation. The project will also raise awareness of the Pasig River's electricity producing potential. For the local government, this study may give a practical product that may be changed to cope with power expenditures and electricity needs. The findings of this study can be utilized as a reference for future scholars interested in 3D printing, hydropower, and water turbine designs. Scope and delimitation. So how in-depth is our study? The research will focus on the design, manufacture, and eventual comparison to existing models of a vertical axis hydrokinetic turbine, which generates energy by being positioned directly on the stream of moving water. The concept is anticipated to be deployed along the Pasig River, where it will harness the river's currents to create enough electricity to light the river's street lamps or for small-scale power generation that is both economical and sustainable. The created prototype will be next compared to the current vertical axis hydrokinetic models and designs on the basis of design cost, size, turbine power, and coefficient. Also, the turbine is not intended to be used outside of the research's objectives.
Chapter 2, Review of Related Literature. This chapter is comprised of existing literature and studies that are used as references for defining and expounding on the concepts involved in the study. The literature herein was used in the establishment of this paper's objectives and methodology. Primary topics include vertical axis water turbine, CFD, additive manufacturing, turbine power coefficient, and the Pasig River. Here, we can see the related literature matrix. According to Guaymel and Lee 2020, hydropower can provide a large quantity of energy when utilized correctly. While in the paper of Brahim in 2014, he stated that incorporating hydropower to the energy mix of the country may help solve its energy insecurity. While according to Mon in 2019, vertical axis water turbines are extremely suitable for river applications, and by doing so, it may help reduce carbon dioxide emissions. In the papers of Yosri et al. And Gao et al., it was stated that in designing vertical axis water turbines, it is important to consider the blade properties or the blade configurations because it affects the turbine's power output and the blade's performance against stresses. Gao et al. Used CFD in order to visualize the structural performance. One example is simulating large eddies. And in the paper of Yosri et al., they used additive manufacturing in order to fabricate the turbine blade, which resulted in reduced cost and reduced waiting time. Chapter 3, Theoretical Considerations. This chapter is comprised of the functioning theories and concepts that present to be relevant to the study. These theories and concepts relate well to the fluid dynamics, namely CFD, ANSYS, hydrokinetic turbine, vertical axis hydro turbine, additive manufacturing, and usage of Pasig River. Reducing carbon dioxide emissions is one of the main motivations for practicing sustainability in the Philippines. One renewable source of energy that can be exploited is hydropower. One can harness energy from the natural flow of water through water turbines. Vertical axis water turbines are the center of this study. The researchers aim to design a vertical axis water turbine using a computer-aided design software, or CAD software. After the design process, the 3D design will be subjected to simulations through computational fluid dynamics, or CFD, and finite element analysis, or FEA, using ANSYS. If the results are found to be satisfactory, the 3D models will be fabricated through additive manufacturing. The turbine will then be assembled, combining all the parts, and be deployed for use in the Pasig River.
For the methodology or how the study will be performed, this flowchart will be using in order to determine the results of this research paper and where we got the conclusions as we stated here to answer the research objectives and questions as stated in chapter 1. As seen here, we have put emphasis on the simulations in order to generate the most efficient turbine, as well as ensuring that the parts will be assembled in order to create an actual prototype that's working. So for the parts, the central shaft is where the blade are mounted, and we're told the blades in place, it rotates and spins together the blades in order to extract energy. The blade, also as flap, as stated, will be made out of 3D printed materials. PLA, this material for extracting the energy generated from the motion underwater. The frame is the rigid material that holds all the heavy parts, all the components, firmly together and supports the load that the turbine itself creates. The LED lamp indicates the status of the water turbine to determine if it's functional or not, and for the purpose of ensuring that the turbine prototype created is working as intended. Designing of the blade for this research, the researchers plan to adopt an existing vertical axis water turbine model to design the blades. The researcher will use CAD software. The use of it presents convenience in 3D modeling and converting the 3D model into different file types. CAD model will entail actual dimensions and build type of the blades. Also make to ensure that the model will be easy to 3D print and convert to shader. To perform simulations after making the CAD model through CAD software, it will then be subject to simulations to determine the performance against stress and pressure, and its performance will then be exposed to fluid movement. The simulations over the study will be done using ANSYS because it's the standard industry standard system for CFD or computational fluid dynamics, or FEA or finite element analysis simulations. CFD to ANSYS, where the simulation primarily used for modeling or simulation of phenomena of fluid flow with relation to the vertical axis water turbine to determine its efficiency while flowing through the water. FA to ANSYS, main purpose is to quantify the structural behavior of the blades. To this simulation, the strength of the blades against the various stresses will be unduly deflections will be determined. Additive manufacturing or 3D printing constitutes for faster rates of production with lesser cost. Additive manufacturing will also allow for much faster, much more economical manufacture of geometrical configurations that are irregular in nature. Will be using polylactic acid or PLA using FDM or fused deposition modeling 3D printers. Assembly, as stated, using FDM 3D printers will be where the turbine blades will be made as a parameters of the blade design. Cannot be manufactured in one piece and would have to be manufactured with respect to the size constraints seen in the 3D printers. Filament, as said, is PLA, stated parameters of blade design. The generator, as the work turbine needs to be converted electrical energy. As a single permanent magnet synchronous generator will then be connected to the drive shaft to convert the work to energy. So we have the permanent magnet synchronous three-phase generator with a capacity of 24 volts per 100 watts. The frame is also various components of the hydrokinetic turbine in one piece. Angular steel, structural angular steel will be used for the frame body, with plates welded in the bottom of the bolts to be attached to fix the prototype on the ground or on the concrete, as stated in the premise of the study. The rest of the frame is TIG welded to ensure structural integrity. Power inverter used to convert raw electricity to standard stable source of electricity. Should create 24 volts of DC power. Inverter will match the creation of that with 24 volts of AC power. Street lamp, since it's required to ensure that the prototype works, series of 12 watts, 24 and 12 volts IP65 rated LED street lamps will then be fitted to the prototype. To test, determine the length of the tip of the blade to the top of the blade sizes. It will be determined using CFD and FEA responses for the because it's required also for the testing analysis as stated there. Necessary tests, we compare to the results of existing turbine blade designs as seen in related literature. Turbine power coefficient for recovered power is calculated by multiplying the airflow through the disk by pressure gradient from across the disk. There is an ideal for power coefficient, say P, which would then be the ratio of retrieved power to available power of the turbine created. For sizing and dimensions, the turbine prototype will be derived from its length from the tip of the turbine to the top of the fixed mount. Blade sizes will be determined to CFD and FEA processes to determine the most compact form while delivering reasonable performance as expected. Thank you very much. That would be all.